There's an E on there that you probably saw and just completely ignored. So there's an alpha E, but that's not the E we're talking about. There's actually a button with E on it. Where is he? Second divides the alpha E, is it not? Yeah, that's the alpha E. Is the who what now? That's the alpha E. We don't want the alpha E. We want the function E. Again, that's the alpha E. Oh, is there actually like an E? Oh, I was thinking because there's E to the X over here. That's one we usually use. Oh, there's an E. Look at that. Hello, E. And you put him in and you get this wacky number. Oh, he is there. Look at that. You can't see that. His name is Euler's constant. And there's a joke. There's a joke that you're not a real mathematician until you understand that word is Euler, not Euler. Euler was a Swiss mathematician, 1600s. So it's pronounced Euler, not Euler. And so he invented this letter E, and he actually chose the Greek letter epsilon. So it's actually not an English E, it's a Greek E. Why did he pick E? Because his name starts with an E. Yes, that's why he picked it, even though it doesn't sound like an E. And just like pi, it's a constant. It's an irrational number that never ends, keeps going, doesn't have a pattern, and it's approximately equal to 2.718. Just like pi is 3.14, E is 2.718. No, there's a decimal. Oh, there's a big decimal. He's this really weird number because he's irrational, so there's kind of no pattern to him, no reason, but he comes up in nature all the time. And he's going to come up in the log applications that we're going to do after the break. So he's just a really weird number that we don't know yet really his whole potential, but he comes up a lot. So instead of writing log base EX, Euler decided, no, I want a new notation because I am so great and my name is Euler. So he decided to write y equals ln x. ln x. ln is the same thing as log base E. So this means all of this.
I wonder how happy he'd be to know that he shares a name with a hockey team that gets the first overall.
Yeah. Considering he doesn't speak English, probably not. Probably not. Yeah. What the ln stands for is the natural log of x.
Is there any special notation for like if the base is pi?
Nope. Only base E gets his own notation. It means the natural log of x. He decided to call it a natural log because, again, like I said, it comes up in nature a lot, and we don't even know the full reason why yet. Why is it not NL? Because that would make more sense. Natural log NL. He's Swiss, and what language do they speak in Swiss? In Switzerland. They speak French, and so it's always backwards in French, so that's why it's ln. You have an ln button on your calculator? It happens to be my most favorite button on the calculator. Who can find it? It's right under your log button. Why is it my favorite button on the entire calculator? Guess. Say it again. What's my first name? I have my own button on the calculator. You don't. Ha ha. Just a note from before that y equals e to the x and y equals ln x, they're inverses of each other, just like the exponential and the log function. So we can graph e to the x just like base to the exponent x. Those are just exponential functions. So e to the x, I'm going to do the same 2 points that we did before. So x equals 0 and x equals 1. If I put in 0, what's e to the 0? 1, because anything to the 0 is 1. And if I put in 1, what's e to the 1? Is e, or 2.718. Still going to have an asymptote, just like any exponential function. So 0, 1 is a y-intercept. And then 1 and 2.718. I'm going to do my dot really big so you can see where I'm putting it.
Right in the middle of nowhere.
Yeah, a little bit higher than the halfway point. And then we know it approaches the asymptote on the left, and it goes up towards infinity on the right. And last year someone was like, oh, that's just a boring exponential graph. Yeah, because it's just an exponential graph with a funky base. How do I graph the ln x graph? Yeah, it's just the inverse of this guy, so we know that the asymptote's going to move to be vertical. So to do the ln graph, we're just going to take these points and switch them. So we're going to have 1, 0, and then e, comma 1. So 1, 0. And then 2.718 and 1. And again, I'm doing my dot really big so you can see it. And we know he approaches the asymptote on the bottom and then goes off towards infinity on the x-axis. And he's just a boring log graph because he's just a log. He just has a funky base.
And because of that, a funky notation.
Yeah, because Euler said so. That's it. That's what they look like. That's it. Oh, a very useful fact. Just follow me here. Imagine I want to calculate the natural log of e. I want to know what that's equal to. So I don't know what it's equal to right now, so I'm going to make it equal to x so we can figure it out. What's the base here that we don't see? What's the base of a natural log? It's e. So I got a little e tucked in there because that's what a natural log means, base of e. So he's going to come over, bump the x up. The log notation is going to disappear. So what am I going to have left on the left-hand side? E. And what am I going to have on the right-hand side? E to the x. Okay, so that's just converting to exponential form. Well, this now becomes a little common base question. There's a little 1 on this e that we don't see, but we know he's there. And if the bases are the same, what can I do with them? I can drop them, so I get 1 equals x. So what that means is that ln e equals 1. Prove it on your calculator. So put ln and then put e and see what it's equal to. When you think that's kind of weird, so you're taking a log with a base of 2.718 and evaluating 2.718, and really those are irrational numbers, so they go on forever and ever, and all that comes out to be 1. How does that happen? All we're going to do is exactly what we've done the last 2 days. We're just going to do equations with e and ln's in them. So we're now solving exponential and log equations, but instead of having a different base, they have base e, and instead of having normal logs, they have natural logs in them. That's it. Yeah, just a natural log is a log with a base of e. That's it.
So basically this is the same as this stuff we've been doing pretty much this whole unit, but Euler or Euler or whatever the heck.
Oh, it's Euler. Oh, it's Euler. Yeah, it's definitely Euler. That's right, yeah, pretty much. Although most mathematicians were, most mathematicians were also crazy, but let's not talk about that point. So you might want your little foldable, because we're going to start to intermingle now, which is exponential, which is logarithm, and your brain's going to start to mix up the steps, so you might want to have that right beside you. So nothing different method-wise, it's just now we've got these e's and these crazy ln's in here. And when we do the applications in January, you'll see why do we need this e? What's his purpose? Why does he show up here? Why was the lumberjack a good dancer?
Sorry for the interruption. We are going to finish up with the last group of grade 10 boys that did not get a chance to do state teams last week. If we could please have grade 10 boys with the last name beginning with the letter S, starting with Singh, William Singh, through to
Why was the lumberjack a good dancer? Because he had natural logarithm. Come on, no, not so much.
Is that the joke sheet for this?
No, it's not. Okay, first thing you need to know when you look at this is decide which of those flaps are we on in the foldable. Is this a log equation or is this an exponential equation? How do you know which one it is? So it's got an exponent and it does not have a log anywhere in it. So that means this is exponential. So open your little exponential flap. What is step 1 for an exponential equation? And all we're going to do differently than what we did yesterday, instead of using a normal log that's a base 10, we're going to use a natural log that's a base e. So I'm going to call natural log each side. That's the only difference in the step. Because there's an e, I'm going to use a natural log. Why? I'll show you in a second. In theory, with any exponential equation, you could use a natural log at any point, because instead of hitting the log button on your calculator, you would just hit the ln button and it's going to give you the same answer. Okay, what is step 2 with exponential equations? Expand using log laws. So what does that mean in terms of this one? Exponent's going to drop down and become a coefficient. And we talked yesterday, because it's a binomial, we're going to bracket it. Oh no. Oh no, we don't have to. Take a look at that. It's equal to 1. That's why we used a natural log, because just log of e does not equal 1. So prove that in your calculator. Just put log and e, and you should get some crazy number.
You mean something like 0.43429444819?
Can we confirm that? But if we use ln e, we already proved what's it equal to. 1. That's the only reason we use natural logs, because it's going to make this a lot easier. So I'm going to just show that this was equal to 1, just so when you look back, you know what happened to the ln e. But in theory, it just made the question a whole lot easier, because now I just have 2x minus 1 equals ln 5.
Wait, what's the ln?
It's a different base. So if we were to look at this, that's 10 to the what equals 2.718.
Oh, that's 10 to the.
This is e to the what equals e, so it has to be 1. Okay, where were we on our steps? So we logged each side, we expanded,
Isolate x.
isolate x, okay? Plus 1. That does not make this ln 6. Okay, that would be ln 5 plus ln 1, so we're adding 1 just like normal. Divide by 2, divide by 2. And the last step with exponential equations? Throw it into your calculator. And you'll notice there's way less to enter than with a normal log equation, because this ln e happened to be equal to 1. Let's see if Shaz can do it. Whew, no pressure. Is that confirmed? Because I heard something else. We're good? Did you get it on the first try? High five! High five! Questions? You notice the steps are exactly the same as yesterday? The only thing that's different is we used a natural log. We didn't have to. We could have used a normal log. You just would have run into more simplifying here. So we chose a natural log because of this little useful fact that it's going to be equal to 1. If you don't like natural log, don't use it. Use a regular log. Just do extra work.
Wait, can you use natural log for the other question?
Absolutely.
Yeah?
It's literally which button do you want to hit in your calculator? Do you want to hit log or do you want to hit ln? It's not going to make any difference in terms of the work.
So then, like, why do we learn the normal log?
Because there's applications we'll do in January that don't use base E, they use natural log. And you're going to see, we're going to do some of the applications. This comes up in science stuff all the time. I think you guys have seen in chemistry already, right? There's an application of logs. Comes up in physics and chemistry and bio and lots of different stuff. Okie dokie, this is an exam question. Imagine you're in exam panic, it's Jan 29, it's like really cold outside and it's smelly in here and you're just grouchy. And okay, first thing you need to understand, exponential or log equation, because you now know the steps are completely different. So take a moment when you see something like this and just pause and think exponential or log equation, and how do you know? How do you know it's exponential? because there's no log anywhere in there. Then pause and ask yourself, normal logs or natural logs? Why natural logs? Because there's an e. So I'm just going to repeat that. The first thing, it's exponential because there's no log anywhere. It's going to be a natural log question because there's e in it. So step number 1 for exponential equations. This is where you tell me. Log both sides. Natural log both sides, yes. Expand. How do I expand? So I'm going to have x minus 1 in brackets times ln e on the left, or ln 3, I should say. And then I'm going to have 2x times ln e on the right.
And ln e just happens to be 1.
Can I do that with ln 3? No, it's only ln e that's equal to 1. So what do I do here? Distribute or not distribute? Why? Brackets are in front. So x times ln 3 is x ln 3. Negative 1 times ln 3 is just negative ln 3. And then I have 2x on the other side. Okay, so step 3 with an exponential equation. X is on one side, numbers on the other. So what would you like to move? Okay. Does it bother other left brains that we moved it to the right? Bothers me too. It's okay. We can do it. We can be right-brained.
So divide both sides by ln.
Go back to your exponential steps. We never divided here. What did we do? We factored. Remember, that was the only way to get this x by itself. So x is going to come out front.
2 minus ln 3. 5 by 2 minus ln 3.
Can I cancel the negative ln 3s? But why not? But there's one on the top and one on the bottom, and then this would be so nice. It would just be a half. I would kill a puppy. And remember, these are always calculator questions. So if you're not using your calculator with an exponential, you've probably done something wrong.
Negative 1.219.
There's the offer. Come on, Josh, you can do it. You can do it. You can do it.
Yeah.
Yeah. Question so far? Are you feeling the connection to exponential that we did yesterday? Right, steps are the same. The only thing that's different is we put an ln instead of a log. Why did we put an ln? Just to make this side easier. Number 3. Exponential equation or log equation? How do you know? Because there's logs in it. So close your exponential flap, open up your log equation flap, because again, the steps are backwards, and until you practice, you're going to want to mix them up. Step 1 for a log equation. Logs on one side, numbers on the other. So what do you want to move around here? ln x, take it over here. Now, what your brain is going to want to do is factor out an ln, because that's what we did with exponential. But ln is a function. You can't factor it out. It's not a number. It's not a variable. You can't just take it out front and leave stuff in brackets. What's the next step with with log equations? Simplify. So this is when we're making it smaller down into one log. What does subtraction mean? So we're going to end up with ln equals x plus 1 divided by x. Can I cancel those x's? Oh, but why not? And if you did, you'd have no variable. And that should be a clue something's gone wrong, because then we have no variable. Step 3. Get rid of the log. And how do we get rid of a log? What's the only way to make log disappear? Move the base over, bump the exponent. What's the base here? It is e. So there's a little imaginary e that's going to come over, bump that 2 up, ln's going to disappear. E does not equal mc squared here. No. I don't even know if the e is the same and it equals mc squared. Isn't what does e stand for? And, yeah, so that's not the Euler constant, I don't think. Because this, although we write it as an English e, when it's epsilon, the Greek e, it's actually italicized. So it is a different e, but we can't write italicized. So. Okay, here's always mass panic. What do I do? Got x's all over the place, blah. People want to start canceling the x's. No. Again, just go back to your bed mass. How do you get rid of a division by x? We just times by x. At this point in any equation, we get x's on one side, numbers onto the other. So what do you want to move? Really bothers me, but I'll do it. So on the right, what are we going to have? People are going to want to do some weird subtraction here with the x's. Nope, can't do anything with this. This is simplified. How do I isolate x if I've got all this stuff going on? Factor it out. How do I get rid of the multiplication by e squared minus 1? Oh no, no touchy. These are non-calculator questions. These are log questions. There's never calculator on these. No touchy. What did we do way back in Unit 1, September, my God, it was forever, when we ended up with something with pi, like pi on 2, or pi on 3, or 5 pi on 6? What did we do with that final answer? We left it. Why would we leave it like that? Because it's an exact value. Same deal with e. E is an exact value. So you're just going to leave this, no calculator. Okay? Log equations never use calculator. We're happy. To a mathematician, that's pretty. That's an exact value. If you decimal that, it makes us uncomfortable.
And I guess I'm not a mathematician.
Not yet. You do know the secret Euler name, but we're not done. That's only step 4 of a log equation. What's step 5? We have to check it. So in our head, we can approximate what the number's going to be. So we know this is 1 over almost 3 squared minus 1. Why do I say almost 3 squared? 2.7, right? It's going to be around there. And what's 1 over 3 squared minus 1? 1 over 8. And that's an ish, right? Because we rounded that. So we know it's approximately an eighth. Check it. If I put an eighth in here, am I okay? If I put an eighth in here, am I okay? What does that tell me about the value? It's good to go. Yeah, there's really no, the only thing is if it doesn't work, you cross it out. Otherwise, there's no work that you show. Does everyone understand why I put 3? Right, because we're just trying to approximate in our heads 2.7-ish, so it's going to be around 1/8. It doesn't really matter what fraction. It's never going to make these negative. You want to do one more before this afternoon, or you want to stop now? One more? Log equation or exponential equation, and how do we know?
Both.
Explain.
There's both in E and logarithm naturel in it.
Okay, well, it's definitely a log equation because there's a log in it.
But
It's also exponential because the variable is where? In the exponent. So this is your first one you've seen that is both. You may want to make a note. This is both exponential and logarithmic. Surprise!
does this make a calculator?
We'll see when we get down to it. What do we do when it's both? How do we know what to start with?
Bed mass.
Yeah, in essence, you're always going to go back to BEDMAS when you solve any equation, and really what we need to do is get that variable out of the exponent. We need to get it out of the exponent into the main equation because that's the only method we have to solve. What's the only way to take an exponent and drop it down? Is you've got to have log. So I'm going to start by logging both sides. So this whole exponent here is going to drop down in front. So I'm going to have ln 2t minus 1. And sometimes the exam will change variables and they won't be x, and that's okay. We just go with t. We're okay with that. And then I would have had an ln e still stuck in there because I dropped that exponent. And then I've got an ln 5 on the other side. You betcha. Bye-bye, ln e. Okay, now what?
Simplify the ln.
How?
Or get rid of it.
Or get rid of it. Okay, we can't get rid of it when there's one on each side. Yeah, this is now just a regular log equation. So the e is gone, so this is a log equation. So what's step 1 of your log equation? Logs on one side. Logs on one side.
Numbers.
Anything without a log on the other. Okay, so I'm going to take this ln 5 over to this side. No, can't do it. Can't do it. I humored you earlier. Okay, after logging both sides, so we're now on the log equation, little flap there. What's the second step to log equation? Smush it down into one log. So 2t minus 1 divided by 5 equals 0. What's the base? E, so little e in here, goes over, bumps this up, ln disappears. So we have that 2t minus 1 divided by 5 equals e to the 0, which is 1. Times 5 to get rid of it, sounds good to me.
It's linear.
Linear makes us happy after quadratics. Like, yeah.
And especially after
Cubics and cortex.
and other stuff. I could probably do
Now we need to check. Where do we need to check? Anytime we had an ln, so here, which is the same as up here. So all I want to know, if I stick in 3 there, is it going to be negative or 0? Positive. So what does that tell us?
Good to go.
Was that not oddly satisfying? Like seriously, all that without a calculator, look what we started with. Bunch of stuff.
No, it's not satisfying because it means I didn't get to use
I know, but how fun is that it's 3? This afternoon we'll finish all the examples and then you'll